Well, hello everyone. Here we are announcing a new product, version 14.2 of Wolfram Language and Mathematica. It's always exciting doing this. I will try and walk through some of the capabilities. I'll also talk about the post that I made today announcing this new version. So actually, it's 176 days since we released version 14.1. We've been planning a twice a year rhythm of releasing versions, and we're right on target here, delivering kind of the latest from our R&D pipeline. And it arrives at a sort of an exciting time for our technology, both in terms of what we're able to implement and in terms of how our technology is being used in the world at large. I mean, I think one of the things that's very notable is increasing use of Wolfram language, not only by humans, the original target market, but also by AIs. And it's really nice to see that all the effort that we put into consistent language design, implementation, documentation, and so on over the years is paying dividends, making Wolfram language uniquely valuable as a tool for AIs, complementing their own intrinsic capabilities. And actually, the other way around is important too, which is our Wolfram Notebook Assistant that we launched last month is a place where we're using AI technology plus a lot more to provide what amounts to a conversational interface to Wolfram language. And I've been using Notebook Assistant kind of all the time, and it's very useful for both experts and beginners alike. But I think the thing that's sort of ultimately most important is the way that it can accelerate the ability to kind of go from any field X to computational X, to be able to kind of take your thoughts and discuss them conversationally and have the notebook assistant crispen them up to make them computational and implement them in Wolfram language. Okay, so let's talk about kind of what's new in version 14.2. The Notebook Assistant we released, it's compatible with a version 14.1 as well, but it's better integrated in version 14.2. The Notebook Assistant in its sort of generic, its simplest use, it's a side chat. You can ask it to do things on the side here. And one of the things that is now a standard part of any Wolfram language notebook is chat within the notebook. If you get a Wolfram Notebook Assistant plus LLM Kit subscription, you can immediately just type a quote and you get something here where we can say, you can start chatting here. You can say, I want a picture of an array of 3D cubes in RGB space. Bit vague. Let's see what it does. Now we're talking to the Notebook Assistant in our notebook, and we're going to get some result, I hope. You never can tell what these creatures do. Okay, so here I can just say insert and evaluate. There I get my result, or I could ask, or I could go on and chat further. So if I'm using side chat, I could say here something like, how do I do that with HSB? And now that will be a kind of a side chat that won't be stored in my notebook. The side chat can look at what I have in my notebook, and it's a place where we're kind of, it's a different flow. I can take this and I can go and say, okay, now insert that into the notebook, and I can insert that and evaluate it. We've got that different result. But the idea is that side chat is something that you're kind of off on the side, talking to the Notebook Assistant, and you expect not to have it part of your saved workflow. In Notebook chat, you expect to have what you're doing saved in the notebook as kind of part of your record of the work that you did. All right, so the in Notebook Assistant chat, there are a few things to know. As I say, crucial thing to know is type a single quote, you'll get a chat cell. Another thing that is relevant is a chat break. Type a tilde, you get a chat break. The chat break makes it forget. So what did I just do? It's not going to know. If I hadn't put in that chat break, it would have looked at the previous part of the notebook. Okay, there we go. If I removed the chat break there and said, "What did I just do?" It will probably not. It will probably be able to say something about what I just did. Okay, you generated two different visualizations of color cubes, blah blah blah. So the chat break is something which says, "Okay, I'm going to start a new topic here. Don't get confused by things that have already happened in this notebook." So that's the second thing to remember is the chat break delimiter type a tilde. Another thing to know is that when you're using any of those uh, chat break or a chat cell, you can go in here and you can start setting things like you can start using a different model. You could perhaps do something within, this is just talking to the raw model that LLM Kit uses, or you can go and if you have accounts with other models, you can do that. You can set parameters like temperature and so on if you want to. But the generic is that you're talking to the notebook assistant, which has been carefully built to really know and understand and have kind of a harness around the wild animal to let it be as useful as possible as an assistant in your notebook, helping you make things computational with Wolfram Language. And the thing to understand about Notebook Assistant is it's a big stack of technology that goes far beyond just talk to an LLM. LLM Kit allows you more direct access to LLM functionality for doing things specifically with LLMs. Notebook Assistant is more about, I just want assistance with the things that I'm doing. I don't care where that assistance is coming from. I just want conversational assistance. Okay, well, let's dive in now to the things beyond Notebook Assistant in version 14.2. I should emphasize with Notebook Assistant, you can get the side chat Notebook Assistant in version 14.1. What's new in 14.2 is the generic in-notebook chat capability available whenever you have a Notebook Assistant subscription. All right, version 14.2. What's new in the core system? The big thing is a construct we call Tabular, which supports big data, big tabular data, and that's integrated into lots of other capabilities of Wolfram Language. I think it's an exciting thing. It really makes it possible to use big data very directly within the language, as opposed to interacting with external databases and things like that. It's something which brings big data, and by big, I mean gigabytes to terabytes type data directly into something you can work with in the language. So tabular is kind of a new fundamental data structure for Wolfram Language. We have lists, we have associations, we have data sets. Now we have tabular as well. So tabular is a streamlined, efficient way to handle tables of data that are laid out in rows and columns. And let's take an example here. Let's start off. Okay. Here we've going to import a data set. And this is in Parquet format. And it is a data set of trees in New York City. And okay, here it is. And we'll have sort of a view onto that data set. If we scroll down here, we'll find there are 683,000 lines in this data set. It's a fair number. Notice imported very quickly. It has a whole bunch of columns. This is sort of the typical form of tabular data, is it's got rows, it's got columns. It probably has lots of rows and a decent number of columns. But that's what that looks like. And it imports there from, in this case, a Parquet file. It could have been importing from a CSV file. We'll talk about importing later. Okay, so now the big idea is that you can manipulate this tabular data in a very direct way. So for example, there's a column here, tree underscore DBH. We can just say, make a histogram of the NY trees tabular with showing me the tree underscore DBH uh, column and make a histogram of the values in that column. So zippingly fast, we're dealing with 683,000 rows, and we're just making that column with this very convenient syntax where we're talking about things in terms of their columns. Okay, so under the hood, you can think about Tabular as being like a very optimized form of a list of associations, where each row is an association whose keys are the column names. So that means that lots of things just work on uh, lots of things just work on tabulars. So here's an example. We can use select, and here we're selecting hash SPC underscore Latin. So that's the value of the column of the SPC Latin column, or alternatively, the thing in every. We're thinking about this tabular as like a list of associations. So what this is saying is select from that list such that the key in that association, the SPC Latin key of each association, is Pinus virginiana. And so we do that, and this will now give us our pine trees. Now, or that particular kind of pine tree, we can also just go ahead and say, what's the length of that? So we're thinking of it as a list of associations. This is just going to give us the list of that, the length of that as if list, so to speak, 10. So 10 pine trees. So now, again, we think of this, we think of it as a list of associations. So now, for example, we can do something like we can say make a counts, count that list of associations by the value of, we could have said hash SPC Latin, or we can just say the string SPC Latin. And this will now give us, for every kind of tree, this will give us a count of the number of times that a particular value occurs for the SPC Latin element of those associations, or alternatively, the number of times in the SPC Latin column that each different tree type appears. Okay, so all right, so let's go ahead and say, let's find out what columns there actually are in this tabular. So column keys tells us not just the keys of an individual association, that would be keys. This is column keys. In a tabular, we're thinking that the columns are the separate sort of elements of every association. Okay, so now if we wanted to, we could just go ahead and extract parts here. So this is rows 5, 6, and 7, and this is the SPC Latin and the tree DBH keys in the associations on those rows. So that's what we get by extracting that. So these are what I've shown you so far are operations that kind of operate on Tabular as if they were operating on lists of associations. There are also lots of powerful new operations that are kind of special to tabulars, although they actually would work on lists of associations, but we've introduced them because they're now really convenient and powerful because we have this tabular structure. So an example is aggregate rows, which constructs a new tabular from a tabular by aggregating groups of rows. So let's take a look at that. So here we are saying aggregate rows by this function it's creating a new column, mean DBH, which is the mean of the tree DBH element, tree DBH column in every row, and we're looking at that grouped by SPC Latin. So we're taking those rows which have the same SPC Latin, and now we are finding essentially for every different tree type, we're finding the mean. What is that? It's some diameter of the trunk of the tree. We're finding the mean within that group that has the same SPC Latin value. We're finding the mean of this quantity within that group. And so here we'll have the mean DBH. We've constructed a new tabular which just has as row keys, we have as row names, we have the values of SPC Latin, and here we have this one column, which is just mean DBH, that's been computed from the mean of the tree DBH column in the original tabular. So, and then we could just take this and we could say reverse sort by, and that just works because tabular is being operated on as if it's a list of associations. Okay, well, we can also take a tabular and turn it into a kind of other type of structure. So, for example, here we're using from tabular and we're making a matrix where we're taking the latitude and longitude columns and we're of things where the value of the SPC Latin key is this pine tree, and we are taking the result of that. We're selecting those pine trees. We're taking the result of that and just making a matrix of latitude and longitude values. So that's, and then, for example, we could take that and we could actually plot it with GeoList plot. And those are the positions of the apparently 10 Pinus virginiana trees surveyed in New York City. Okay, so before I go into more detail about tabular, and I'm going to talk about tabular at some length here, I should address the question, when should you use a tabular rather than, for example, a data set? So tabular is specifically set up for data that's arranged in rows and columns. And it has lots of powerful operations that make sense for data in that rectangular format. Data set is more general. It can have an arbitrary hierarchy of data dimensions. And so in general, it can't support all those rectangular data operations of tabular. So in addition to being more specialized for rectangular data, that allows tabular to be much more efficient. And actually, we're doing all sorts of modern, wonderful things to make the data handling in tabular blindingly efficient. And those are things that are specific to rectangular kind of row and column type data. Data set that allows deeper hierarchical data can't make use of those things. And many of the operations that we can define in a very clean way for that row column rectangular data, we aren't as well defined for this more general data set structure. Now, you can convert between data sets and tabulars very easily, but you can do slightly different things with them. Okay, so let's see sort of why tabular can be so efficient. There's a function tabular structure, which kind of looks a little bit under the hood at what's going on. So here's kind of what's happening. We've got the keys of the columns, and now we have this thing, which is the column type. And we have counts of missing data and so on. But it's important that the way a tabular works, another special feature of tabulars is that in a tabular, every element in a given column is set up to be the same type. So it can be an integer 64, it can be, these are low-level types. They're actually the same types that are used in the Wolfram Language compiler, and that's sort of how this is being done, is but once we know it's of that type, we can be sort of blindingly efficient in operating on that. And there are always exceptions when it's mostly integers, but oh, whoops, there's a place where there's missing data or something like that. There's a whole mechanism for dealing with missing data in tabulars. We'll talk about it a bit more later. But that's how it can sort of be blindingly efficient. It kind of is, oh, it's all this type of data, and I'm going to deal with the exceptions separately. Okay, so in the one way you can use tabular is operating on in-core data. So you're moving everything into memory. We'll see ways in which you explicitly do that a bit later. But you can also quite transparently use tabular on out-of-core data. For example, data that's been stored in a relational database. So let's see if we can do that here. So this is now using a file-backed relational database. Here we go. Now tabular, in what I've shown you for in-core tabulars, it immediately shows you this kind of preview of what's in the tabular, so to speak. For out-of-core ones, it doesn't by default do that. It just says there's a tabular, there's a relational database that's backing this tabular, and it has 13 columns in this particular table. Okay, so now we can go ahead and use the same kind of operations we were using before. So we can say column keys, and that's now going out to this relational database and looking up the columns in that relational database. And you can do things like you can say, take largest by, one of the columns was credit limit here. So take the three largest three largest rows by credit limit in that tabular. It's still an out-of-core tabular. So actually that operation that I just asked to be done, take largest by, was compiled into an operation that can be done directly on the out-of-core database. If I wanted to, I could pull this into memory so that I can operate on it in a sort of in-memory way. And there's a function to memory, and there was a little tiny delay there as it was kind of sucking that stuff out of the relational database and putting it into the actual in-core memory of my Wolfram Language session. And now I've got a tabular again, but now I've got an in-core tabular. And for example, I'm in a position, I think we only asked for 3 here. I'm in a position, it'll show me the preview and I can do all these operations on it. Okay, so that's sort of a rough go through of tabular. Let me now dive in a bit more detail and start showing you some of the capabilities of tabular. It's really worth learning tabular. Tabular is very powerful. You'll see a bunch of things that you can do with tabular that are relevant even when you're basically dealing with small data, but when it really comes into its own is when you have much larger amounts of data where it can really shine. Okay, let's get a tabular. This is a sample tabular involving penguins. Okay, and that came from the data repository. The data repository, as of today, has a whole bunch of data in tabular format in it. We'll talk later about import in version 14.2. Now has the ability to import things as tabulars, even when in the past they would have come in as lists or data sets or whatever else. So here's a tabular of penguins. Seems like there are 333 penguins here. And we're going to use this as our sort of sample for how you can operate on tabulars. So for example, here we can just get the last 2 penguins in the list. There they are. Or for example, we could say, let's sample 3 rows at random, because remember, a tabular is as if a list of associations. So the random sample is sampling from that list and giving us, in this case, 3 associations, 3 rows of the tabular, but it comes back as a tabular. So now we can go in and do some slightly more elaborate things. We can say, take the largest by in that list of associations, take the rows, the list elements, for which are largest by, and this is now going in and looking at keys in the association by bill length and flipper length, and get the 3 largest of those. So now those are the 3 largest penguins by bill length and flipper length. Now, if you look at this tabular, you'll see some tricky things. So this, for example, the bill length was in millimeters, but it knows that it's just going to treat these internally as just numbers, but it knows that all of them, it has a container that knows that, yes, this has units of millimeters. So if I were to turn this back into something like a list of associations, those would come out as quantities. But here in the tabular, it's being very efficiently handled in a way where it sort of gets to think about these things as just a column of numbers without having to worry about the fact that, oh, actually, they're all millimeters and so on. Okay. So, by the way, something I actually didn't even remember that we'd made work is you can say hash and then just quotes and then the name of the column. And that's something that just like you can say hash name here, and that is equivalent to hash of quotes name. That's sampling the name key in an association, in a particular association. This is an equivalent way to do that. And it turns out even when you have kind of unwashed column names that come from the outside world, for example, that have all kinds of things like underscores in them, you can deal with that by just using this syntax of hash followed by quotes. Okay. So quite often you don't even have to use the hash thing. You can just use the string, and this is equivalent to hash quotes body mass, and this is sorting the penguins by their body mass. Okay, so um, let's we talked so far about what you do selecting rows from a tabular, sorting the rows in the tabular, those kinds of things. But what about dealing with columns? Okay, first important sort of tabular special construct is construct columns. So this takes the tabular penguins and constructs a new tabular, which in this particular case is just those two columns from the original tabular. So this is essentially extracting the those columns in from the original tabula. But construct columns doesn't let you just say, oh, I just want the things in that column. It allows you to apply an arbitrary function to any collection of columns. So in this case, we're constructing columns where we're just taking species, and then we're taking another column. We're making another column called letter, and that's a string take of the species name, the first element. And then we're having another column that's called billing, which is another function applied to effectively each row of the tabular, computing the bill length plus the bill depth. And there's the result. So this is now constructing a new tabular with constructed columns where we're specifying each of the constructed columns. Here we're just using the species column, we're copying it over from the previous tabular. Here we're naming a new column, letter, and we're giving a function that computes the values in that new column from the existing tabular. Okay, by the way, here's a trick that I should have known years ago, but you can this is a way of dealing with the kind of syntactic aspects of using rules with functions. Because if I were to use a just a straight function here, I put ampersand here, you can see when I press that ampersand, you can see from the flash it is the precedence of ampersand is quite low. So the whole rule will become a function. And I'd have to put parens in here to indicate that I only want that function to be the right-hand side. But you can kind of a convenient typing way to avoid that is just to use the explicit function syntax here. So you don't have to remember to type the parens and all that. Just a convenient thing. And now with tabular, one's using a lot of rules with functions on the right-hand side. So this is a thing worth remembering. Okay, next construct, transform columns. So construct columns lets you start from scratch and construct a tabular with particular columns. Transform columns lets you take an existing tabular and do things to its columns. So for example, here we're taking, we are transforming the species column of penguins, and we are transforming it by applying the function that just says take the first letter, first of the thing that's in the species element of each row. And so here now we're transforming these columns. So now we've got the species column. Instead of listing the full name of the species, it just lists the first letter in the species name. Okay, transform columns also lets you add new columns. It lets you specify the content of the columns like construct columns. But one obvious question is when you're creating a new column and you're sticking it into the existing tabular, where does that new column go? Well, by default, they go at the end after all the existing columns. But you can, if you specifically list an existing column, that's kind of used as a marker to determine where to put the new column. And you can also do things like say a particular, well, here, I'll show you. You can say here we're doing something where we say index to nothing, that will delete the index column. Now we're mentioning the species column, so that's kind of a marker for where to put the next column we mention. The next column we mention is a new column, letter. Then we're saying now bill depth comes along, and now we're putting a new column billing after bill depth. So this is now the transformed tabular in which we have the letter is being added here after the species, and billing is being added here after bill depth, and the index here, that's probably the number of that penguin, is being deleted. Okay, so that's how we can use transform columns to transform a tabular. Okay, well, the things we've talked about so far, they all operate separately on each row of a tabular. So first we were doing operations that were really row-oriented operations. Now we've been doing column-oriented operations, but everything we're doing here is kind of looking separately at every row of the tabular. Now, there's also the question, well, what happens if we just want to gulp in a whole column to use in our computation? For example, let's say we want to find the mean of everything in the column in the operations we're doing. Okay, so there's a new construct that will show up elsewhere in the language as well. It's called column-wise. And this is saying, let's have a D bill, which is the bill length minus the mean of the bill length, where the mean of the bill length has been computed column-wise. So that means that it takes the whole column here and it computes, this is being computed across the whole column, what the bill length is across the whole column. We're computing the mean of that. We're using that in this function. So there we get the result. Okay, so effectively column-wise lets you compute a scalar by applying a function to a whole column. So it gulps in the whole column, makes a scalar, makes it just a number or something that you can then use in every element of every row that you're generating. There's another function, column-wise thread, that lets you compute a list of values that will in effect be threaded into a column. So column-wise value goes from a whole column down to a single number. Column-wise thread lets you take a collection of numbers and kind of thread them into a column. So let's take a look at that. So here we've got total weight, and that is a column-wise thread of an accumulate. So column-wise, so the accumulated body mass is accumulating successive values, and now column-wise thread is taking those successive values that we have as effectively a list of values and then inserting them, threading them into a column, so that what we get is we going from that list to spray it out into this column. Okay. So, by the way, if you've just got a list that you've got completely externally and you want to insert it into a tabular, you can use the function insert columns. I'll talk about that a bit more later. Okay, another big concept in dealing with tabular, and there are a bunch of new concepts in dealing with tabular, but another very useful concept in dealing with tabular is the idea of grouping. So in our penguins, let's look at our penguins again. Okay, in our penguins, we've got an individual row for each penguin of each species. But what if we wanted to aggregate all the penguins of a given species? Say we're computing their average body mass. Okay, for that, we use a function called aggregate rows. And what aggregate rows does, it works like construct columns in the sense that you specify columns and their contents, but unlike construct columns, it creates new aggregated rows rather than just taking every row in the original tabular and making it a row in the final tabular. This now aggregates rows. And what it's doing is it's aggregating rows, grouping them by species. And so if we look at the first column here, what we'll see is that it has a gray background, and it's what we call a key column, a column whose entries, perhaps together with other key columns, can be used to reference rows. It is a unique key for referencing rows. So we'll talk some more later about how you can use row key to indicate a row by giving a value from a key column. So instead of selecting penguin number 6 here by looking at its explicit number here, we can take in this kind of tabular with a key column, we can then say just take this and use row key adeli and compute the average weight from that, and we'll extract that element. Notice that it knew to wrap it with a grams quantity and so on here. Okay, well, let's continue aggregating. So let's say we want to aggregate not just by the species, but we want to distinguish penguins by species and what island they were on. Okay, so there we give two grouping elements. And what we'll see here is that we've got two key columns, a species column and an island column. And so this is now telling us not the average weight of penguins grouped by species, but the average weight of penguins grouped by species and island. So it's the Adelie penguins on Torgerson Island, the Adelie penguins on Biscoe Island. Separately, those are now separate groups, and we've computed the average weight for each of those separately grouped collections of penguins. So, in a sense, what we have here is a table whose rows are specified by pairs of values. Here, species and island. But so that's a way that we can specify things. We're saying the things, the group, which is Adelie and Dream, has average weight this, and so on. Okay. Another important concept is to take this and pivot things so that these values of species and island are used respectively for rows and columns. Okay, so let's go ahead and make a pivot table here. And so what this is doing is it's now taking species and using that for rows and island and using that for columns. So it's the same information that we have here. We're saying we want to know Adelie penguins on Torgerson Island, their average weight here is 3708 grams, etc. And this is now, it's just taking what was a thing where we were labeling each individual row with these two attributes. Now we pivoted that so that we're labeling rows by an attribute and columns by an attribute. And when we do that, well, it turns out there are no Gen 2 penguins on Torgerson Island, at least when somebody came in and figured out how many penguins there were in different places. And so that is a piece of missing data. And in the pivot table, we see that as a missing element there. Okay, so normally pivot table gives the exact same data as aggregate rows, but in a rearranged format. So there is an additional feature, several additional features to pivot table, but one of them is this. It is to include group aggregates. And so what that's doing is it says, in addition to giving these individual, how many penguins, Adelie penguins are there on each of these islands, it also gives us a total, which says how many total Adelie penguins, what's the result for all Adelie penguins sort of aggregated over these islands. Okay, so let's see. If we are using aggregate rows, we can, this was in this pivot table, we've got just one quantity. This is the body mass, the mean body mass. Here, we've got, when we're aggregating rows, we can aggregate rows with multiple quantities, here average weight and max bill size, aggregated with these groupings to species and island. Now, pivot table can deal with this. What does pivot table do when we try and pivot? So remember, before we just had two attributes, the species and the island, and the pivot table was constructed with the species corresponding to the rows and the island corresponding to the columns. But now we've got a pivot table with we've got and each entry there was just a single value. Okay, so now what does it do when we have two quantities? Well, now we're again using species of rows, islands of columns, but now there's doubled up columns here because there's one column which is the average weight column for penguins, Adelie penguins on Torgerson Island, and another which is the max bill column. So that's what pivot table does if you have multiple columns there. Okay, so if we want to extract an element here, again, this is a sort of a tricky thing, a new concept, the notion of an extended key. We can extract with row key Gen 2 an extended key average weight Biscoe. that will now go ahead and extract that number there, because it's basically that extended key is representing that whole header of average weight Bisco. So there we get the result. Okay, let's talk about how you get data into Tabular. Well, you can import it from a file, a CSV file, an Excel file, a Parquet file. You can also import it from an external data store like S3 or Dropbox or whatever, and you can also import it from a database, or you can get the data for a tabular directly from Wolfram Knowledge Base, like from our entity framework, or from the Wolfram Data Repository. So it's important that there are many functions. So if you just take a list of lists and you just wrap it with tabular, it will turn into a tabular. And if we say normal, it will go from the tabular back into the list of lists. Okay, so you can do the same thing with sparse arrays. Here's a sparse array with 1 million, which is has 1 million rows in it. There it is as a tabular. Notice how quickly it came in. There's the sparse array 1 million row tabular, and if we see how is it stored, well, what's the byte count of that? It's 80 megabytes. It was created really quickly, and it's very efficiently stored. So let's look at, I said that a tabular is as if a list of associations. Well, let's actually take a list of associations and make that into a tabular. Here's how you do that. Very simple. And you can also do that in tabular. This is taking the list of associations and just saying tabularize it. Now what we can do is we can say, okay, here's a tabular where I listed separately the inner data, 1, 2, 3, 4, as well as the column names. That's another way of specifying a tabular and getting something into tabular form. So you might have something which is a pure, essentially, array of values, and then you want to effectively name the columns in that array of values. And you do that by taking the array of values as the first argument of tabular. The second argument is the names you want to give to those columns. So this is kind of a way of creating arrays with named columns in the arrays. Okay, you can also convert a tabular to a data set. This is that same thing as a data set. And you can convert a data set to a tabular. Now, of course, if you have a data set which has hierarchical data deeper than just rows and columns, what will happen is the tabular will have to take those sub data sets and it will make the row and column layer of the data set, the top row and column layer will become the rows and columns of the tabular, and then the elements of the tabular will actually be expressions which are the sort of inner data set that corresponded to those hierarchical pieces. Okay, so in general, so this is sort of the default way of taking something like a list of associations, converting it to a tabular. In general, there's lots of options for how that can work. So, for example, this is a particular case of two tabular where we're specifying the rows of the tabular separately here, and we're telling it this is the columns way of creating something from that list of associations. Okay. Well, if we look at CSV files, for example, comma separated value files, if I looked at that file, it would just be a piece of plain text. Now, import now has a tabular import element, which says, okay, import the CSV file as a tabular. So here we have the result. This is, I guess, trees in Champagne, 27,000 of them came in nice and efficiently from that CSV file. You can have CSV files with millions of entries if you want and just pull them right into tabulars. And tabular in a CSV file, it doesn't really know what the elements are. So it has to guess that this is a column of numbers so that it can have its whole story of, if I say tabular structure here, it'll have its whole story of what it thought those column types were: integers, strings, whatever else. And it does that. It efficiently tries to figure out what type of data should it be storing this as that allows it to store efficiently and manipulate things efficiently. Okay, so in addition to CSV files, there are other kinds of imports you can do. Modern columnar data formats like Parquet, ORC, and Arrow, they're all imported very efficiently into tabulars. You can also you can perfectly well import things from URLs or URIs, and it goes through the whole authentication system. So if you have a URL that's some corporate data thing that requires some kind of authentication with any of the methods of authentication, username, password, OAuth, any of these other authentication methods, you can just tell import to go there to turn it into a tabular, and that whole mechanism of authentication will be handled by the standard mechanisms in the language. Okay, so for example, there's a new type of thing that is not just a file that's being imported. It's something we call a data connection object, which is a symbolic representation of remote data, sort of encapsulating all the details of how to get to the data. So for example, you can have a data connection object for an Amazon S3 bucket. Here there is one, and let's see what happens if I run this. Okay, this has already been authenticated, so it knew that it could just access this bucket, and there it is. There's the data connection object. That data connection object is a raw symbolic thing that represents the data connection, and now I can go to that data connection and suck the data in as a tabular. So in 14.2, we are supporting Amazon S3, Azure Blob Storage, Dropbox, and IPFS, and we're planning support for all sorts of data warehouse connections, APIs, and so on. Okay, what about data that's too big or too fast changing to make sense to explicitly import? That's when we get to start using relational databases. Let's see. Do I have this? Humph. It's odd. Well, let me show you some examples here. Well, here, I might be able to do this. I don't know whether this will work. Oh, I see. Okay, I think this is not stuff I can show in real time because it requires. I'll show this from the post that I made. So this is now accessing an external database. There's a database reference to that external database. This is a very big external database. This is a multi-terabyte external database. This is what it looks like to refer to that relational database and this particular table in the relational database. Now I'm turning that table into a tabular. And for example, that table is 158 million rows, 86 columns. And this is part of OpenStreetMap. And we can, for example, we can pull into memory the first 3 rows and 10 columns of that thing. If we tried to pull the whole thing into memory, we'd probably run out of memory. This is being handled in an external database, not even on my own machine. So then, as I was indicating earlier, one can do lots of operations on the external database where they're compiled into effectively, in this particular case, SQL, running on the external database. So you type Wolfram Language code, what actually gets done is a query to the external database. So here we're doing a select of entries in this database that correspond to strings in the name column of that database, where the string in that name column contains the characters for Wolfram. So now we're specifying that select, but it's really just queuing up a bunch of SQL queries. It doesn't really, in order to actually see the results, if we say to memory, we'll actually do those queries on the external database and then pull the results back into our Wolfram Language session to see them. Okay, so in this particular case, we are getting to memory of delete duplicates of construct columns of that database where we found all the rows whose name column has a string that contains Wolfram. So now we construct the columns, and this is basically telling us all the streets in the world that have Wolfram as part of their name. Calais Wolframita seems to be one of them. And so it turns out there are 58 Wolfram named items in this database. Okay, so that's using Tabular as a wrapper that lets you operate in Wolfram language, but have queries done in the external database, and then pull the data into an in-memory tabular when you need it. Okay. Well, another place to get data for Tabular from is from our entity system, our knowledge base. And so here we're asking Central American countries, we want population and area. Oops, I pressed that and it gave me help. We'll go population and area as a tabular. So now this is going to our knowledge base, our curated knowledge base, and it is getting as a tabular the population and area of these different countries. Okay, so we can go on and see more, I'm sure, here. Why are we not? Maybe that's all. Oh, that's all there are. Okay. Also, as I mentioned earlier, there's starting to be lots of tabular data. You can take a data set in the Wolfram data repository, and it might or might not immediately be in a tabular format. Here, there's a data set it's probably in a data set format, and now this is retrieving it as a tabular here. This is rat sightings in New York City. I think we might be using that in a little bit to look at some other features of Tabular. Okay, so that's a little bit on how you get data into Tabular. Okay, one of the features of data in the real world is it's got lots of messy stuff in it. So how do you how do you clean the data so that you can really use it in a computable way? You know, years ago, I defined this kind of hierarchy of computable data. What level of computability has been reached in that data? From basically, you've got the data, it's on index cards or something, to it's in digital form, up to all sorts of things where you do repeated systematic computation and so on. Okay, so let's see how you do that data cleaning with Tabular. It's nice and clean, not to make a pun. So let's take an example here. We are importing some data, CSV file data, in tabular form. So here's our data. And now the question is, well, sometimes, well, here it's finding in that file, CSV file, it found that there's some nice data in this column, but there's some data it didn't understand or whatever. It treats as missing data here. Okay, so first question is, well, what did it actually find? When it pulled this data in, what did it figure was in the data? Okay, so here is the inferred column types. So for example, here's a time column. It guessed that column was a column of times. It guessed that the wind speed was in real 64 numbers and so on. And it counted a certain number of missing data elements in these different columns. Okay, so there's an ID column here. Looks pretty irrelevant. Let's just get rid of it. Okay, so let's just say delete columns. Data is delete columns of data comma ID. Okay, we've gotten rid of the ID column now. Okay, the first two columns here are date and this time are being, well, let's see, the time is being identified as a time, but the date was just identified as a string. But actually, we want it to be interpreted as a date, and actually, we'd like to combine the date and time. So let's do that by transforming columns and making a time column that is the combined string turned into a date and time object. Oh, and then once we've done that, we want to get rid of the date column. We're going to make the time column be this nice combined date and time, and then we're going to get rid of the date column, and that's how we do that. Isn't this stuff very nice and clean? It's very took us a long time. Some of you may have watched some of the live streams that involved many tens of hours of design work coming up with all these mechanisms for Tabular. And if you look at sort of what went in at the beginning versus what came out in terms of design, I think it's rather impressive how clean the final design ends up being. Okay. Well, here, let's say we want to keep doing data cleaning. We don't like the fact there's wind underscore speed. We just want to call it speed. And we just want to call the wind direction direction. So we can just say rename columns. Now we've renamed those columns. You see that here. And now, for example, let us go ahead and deal with the fact that these are just numbers, but really these things are being measured in certain physical units. So for example, here we are taking the pressure and we're saying it's a quantity in millibars. We're taking the temperature, oh, just for good measure, we're converting it to degrees Celsius. No, we're converting it to degrees Fahrenheit. So let's go ahead and do that. Now we've converted, now we see at the top here that there's a little thing that says degrees F. That's saying all these numbers are really interpreted as degrees Fahrenheit temperatures. Okay, so now let's go and start actually doing things with this data. So here's a cool thing we can do. We can take that data and we can just plot. This is a dateless plot of time against temperature. And this is all we have to do to take the data from the tabular and plot the values in the time column against the values in the temperature column. And there we get the result. It's so we don't have to go and figure out how we're sampling rows and columns and things. We just go into this. And by the way, this works for lists of associations and data set elements just as it works for tabular. So this whole mechanism of being able to say we have data and then using this arrow syntax, rule syntax, and then giving the names of the columns, we can do that to extract this data and, for example, make this visualization. Okay, so let's take a look at some more stuff here. So let's say we want to select from that data, station is KJFK, and then do the same thing. There's the result specifically for that particular, this was taking all the data as a function of time, even though I think there are multiple airports here, and this is weather data for different airports. Here we're just selecting the station. The weather station was the JFK Airport weather station, and then we can plot that there. Okay, well, why is there a break in the curve? Well, we can go look at, that is December 11th. So let's go scroll down here, scroll. Lots of data here. If we scroll, or maybe I need to just, oops, December 11th. Okay, so what we'll see probably there is that okay, KJFK has missing data there. So that's why there's a break in that curve. Okay, what we can do about that? Well, we might want to fill in that missing data. So this is where we can, well, let's select the JFK data alone. So we just say select station is KJFK. And now we've got a powerful function, transform missing. This says take the temperature column and transform the missing data by interpolating it. And there are different ways you can transform the missing data. You can specify lots of kinds of, you can specify your own function for filling in the missing data. You can use all kinds of fancy machine learning and so on. But now, when I do a dateless plot, it will show that temperature, which was previously a break in the curve because it just didn't know the value. Here, that break in the curve will have been interpolated because that's what we told it to do to fill in the missing data. So that was transforming the missing data by interpolation. Okay, so let's see. Yeah, so here's a one thing that's a bit mysterious about this plot is that it extended the plot further than we had it before. So it went to December 12th before, now it's going to December 13th. And essentially, it's going out into the wild blue yonder, kind of interpolating from what it knows, but actually there was no data there. So we might want to just say, let's make an honest plot. Let's simply discard data where there is, for example, discard data from every where basically nothing was measured. I think if we go down here, we'll find out. Yeah, there's a row where basically nothing was measured here. So here we've got a new function discard, which goes along with select. We're going to say discard data where the count of the number of missing elements was more than 3. So then with that having been done, we've now cleaned the data further. We've gotten rid of those elements which basically had very few measurements. And now we can plot that data and we don't have that overhang at the end. Okay. And okay. Well, sometimes there's data that actually is missing. Sometimes there's just data that's somewhat more insidiously just wrong. So let's, for example, make a histogram in our JFK data of the pressure data. Okay, well, that's well and good. There's pressure around 1,000 millibars or whatever. There's also something down here with a pressure below 200 millibars. Unlikely. The airport didn't go off into space. So maybe there are transcription errors in the data. We don't know. But what we want to do here is we can remove those anomalous values by using not transform missing, but transform anomalies. And so this is using transform anomalies, trimming data that is sort of anomalous in value. And there's sort of lots of machine learning stuff we can do to define what it means to be anomalous. But here we've trimmed the anomalous data. So now we may make this histogram of pressure. We'll just see the reasonable pressure values. We can also get transform anomalies to try and fix our data, fix the anomaly data. So here's a specification where we say pressure. We replace the pressure with the previous element. So as we go down the tabular and we see a particular pressure element that is anomalous, we just say, okay, throw that out, replace it by the previous value in the list of values. So then we'll get something again that is slightly different from what we had before, replacing the anomalies that way. You can also tell transform anomalies to just flag anomalous data and make it missing. Well, now there's a question. Let's say you got a bunch of missing data. How do you do computations on missing data? What's missing times missing? Things like this. Okay, there's a new function that is called missing fallback. If it has an initial value here, and it is telling us it has a sequence of values, and what it will give back is the first value in the sequence of values that isn't missing. So here, missing fallback of 110 minus 10 will give 110 because 110 is a fine value, it isn't missing. Missing fallback of missing minus 10, it'll ignore those two missings because they're both missings, and it'll fall back to whatever the next value was that wasn't missing. So that's the result. So now we can use missing fallback in our data set. For example, we can say, okay, we're going to make in JFK data, we're going to make a column, we're going to transform columns with a thing we're going to call north speed. And north speed is going to say, if the wind speed was missing, make it 0 kilometers per hour. So it's a missing fallback. And if this quantity here is missing, then replace it with 0. Okay, so this is now replacing all the missings. Here we saw some missings there. They're all replaced with 0. Okay, so that's a little bit on how we clean data with Tabular. Let's keep going. Talk a little bit more about the structure of Tabular. We're going to be out of Tabular eventually here, and we're going to be talking about other features of version 14.2, but I really wanted to give people sort of a slightly deep dive into Tabular because I think it's really important, and it's kind of the most important new feature of version 14.2 and something that I expect a lot of people will want to use for data science, many other kind of data-related purposes going forward. Okay, so again, let's say we've got a tabular and we say normal of the tabular it will by default turn into a list of associations. As I keep on saying, a tabular is like a list of associations. So here we've got tab equals that tabular. And now the question is, well, what is a row of that tabular? What actually is it? Let's ask for the second row of this tabular. Oh, it's a symbolic construct called tabular row. If we apply normal to that, we will get the underlying association that is that row. But there is a higher level of that, which is the symbolic tabular row object, which has lots of other metadata in it relevant for dealing with tabular data. So now what happens if we extract a column? We say all the elements, this is sort of traditional data set like extraction. Here, if we extract a column, we'll have a tabular column construct. And in that case, in the tabular column, normal of a tabular column gives a list. Okay, we can create a tabular column from a list. Here's a plain list, and it's now being turned into a tabular column. And now, if we say insert columns, we can say the X column we bring from the outside as a tabular column, and it kind of knits that tabular column into the entries in this tabular. Notice in insert columns, we're saying where to insert it by giving B as the kind of marker column and saying this column is going to come right after the B column. Okay, well, what is a tabular inside? We've talked about that a few times in a few different ways. This is, here's a tabular. Actually, we're kind of revealing a bit about but this is it as a list of lists that we created it from with two tabular, but that's the tabular. We can look at the tabular structure. We see it's this list of different types of columns. And the one thing to realize is that when we look at tabular structure, it's telling us about the tabular column by column. So that reflects the fact that tabular is fundamentally a column-oriented construct. And that's part of what makes tabular so efficient, is that within each column, everything is uniform. Everything has the same type of data within each column. And okay, so let's just see what the efficiency of this column-oriented kind of factored data, where we don't have for example, quantities, things like that, are factored out of the actual data sort of inside the inner workings under the hood of the tabular. So let's take the New York trees data set, and we will import it, and then we'll ask what's its byte count. And this is now that's 373 megabytes. If I now, boy, this might be a problem on my computer. Let's find out. If I make normal of NY trees, we'll get an explicit list of associations. And now let's see what the byte count of the not nicely optimized in tabular is. That's going to blow everything up. It might blow everything up. I'm getting a little nervous. I ran the example for my post on a different computer. That's a bit, oh, there we go. Okay. So that's 5 gigabytes. And if we say, it's about 14 times larger than the version that is purely inside Tabular. So Tabular is 14 times more efficient for this particular collection of data in storing the data. That's a big deal. Okay, if we look at the column types here, remember I said column, I could get column names. This is column types. These are types that are compiler types in the Wolfram Language compiler. And it means that we can efficiently do all kinds of operations on this. One of the things we can do is to cast a column to a different type. So let me show you how that works. This is a low-level operation. It's a casting operation. It says in our tabular, in our tab, this was our tabular, where is it? Our tabular here. Column B was an integer 64, but we want to actually cast that column to a real 32. This is low-level operations, and they're really not something you need to worry about, except for really optimizing how things work with tabulars. But now we cast that to a real 32, so you see here it displayed in that way. By the way, I might mention that these little indicators up at the top here are indicators of the type of the column. So that's a string column with little double quotes. That's an expression column with a little open bracket, close bracket there. And okay, let's see. Talking about missing data. Well, I talked about how we use missing data a bunch, but this is the column. For B, we see that banana has missing data in column B, and we'll see that the normal of that column is 70, 25, and then a symbolic missing. But you can operate directly on that column of the tabular, and then, for example, you can compute its total. And the total, well, it ignores the missing data because, well, it's missing. So there's nothing to total up there. So you can do operations with things like total that work independent of the missing, so to speak. Let's see. So when you import data, there are all kinds of tricky things about missing data. When you know that in the data you're pulling in, -100 represents a missing data element, you can just use missing value pattern in your import to say -100 is the missing value pattern, and so that will be turned into a symbolic missing that will be handled correctly by the tabular system. Okay, well, there are all sorts of other subtleties. I'm not sure whether I should dive into all of them, but let me look at a few here. This is a tabular. We can pivot that tabular so that we now have the coordinates and values are the pivots, but now we've also got objects here, and these are, so now we ask, what's the structure of this tabular? So we can ask, what are the column keys in this tabular? Well, how's it going to represent those second columns? It represents them with an extended key object, which says, well, they're values, but they're values, X values and Y values. That's how it represents that kind of hierarchical extended key. Okay. One more subtlety about key columns. So oh yeah, we can extract things with extended keys and so on. Okay, let's get another tabular. Here's another tabular, and this fruit column has the feature that every entry occurs only once. Apple and pear, a banana appear only once. So we can use it as a key column, and we can do that by saying in this tabular we want the key columns to be fruit. And so now notice that the fruit, it didn't need to number the rows anymore because it could use the name of the fruit as the label for the rows, and it put a gray background here, it turned that into a key column so that it's using the entries in that column as keys for the rows. So now, for example, we can use a row key, we can take ktab and we can extract the pear row and ask for its color, and we get green and so on. You could also use an association to extract, instead of the row key pear, you can explicitly say, this is the fruit column, and I want the pear value for the fruit column. Okay, so a thing that's quite often convenient is to pair columns together, or to combine multiple columns together as keys. So let's say you have a database of people, you've got a first name column, you've got a last name column. You want to make sort of a unique key by combining first and last name columns. So here we've got a key column that we're combining color and count to make that a combined key column. And then in that case, you can with those as the key columns, you can reference a row by giving a row key that is a combination of yellow and 10, and then asking for the fruit corresponding to that, and we get banana. Okay. Well, one of the things that's a story of Wolfram Language is we introduce new structures, we introduce them everywhere in the language, and with Tabular, that's what's been happening. So for example, let's take our penguins again. We can, all these functions, visualization functions and so on, let's make a smooth histogram of the bill length and the bill depth for those penguins. There it is, just works. Using, again, this extraction mechanism for columns from the tabular. Or we could say, let's make a list plot of the body mass and species and so on. We could go ahead and we can do some machine learning. We can classify penguins. We can make a classifier where we're trying to figure out, based on the data about a penguin, what species is it? And now we could say, okay, using that classifier, I'm telling you, here are these various attributes of the penguin. What species is it? Okay, it's an Adelie penguin. Okay, now we could do something like a feature space plot where we are, that's cool, where we're taking all the features of penguins that we know about and we're labeling by the species. And now we're seeing that these different species break into different regions on the feature space plot. Probably those different Gen2 regions correspond to not only islands in the feature space plot, but islands in the Antarctic. Okay, we can do fancy things like we can say, make a let's make a fake penguin. So let's learn a distribution and then let's make random variates based on this distribution. So we learnt the distribution of penguins, and now let's make 3 random penguins that aren't real penguins. Whenever people do that with their data, it's a tale of sin. But there are reasons why one wants to sort of sample, for example, for augmentation, for machine learning, and so on. One wants to sort of make more data that's like what one has before. Okay, so that's the story of Tabular. I think it's really exciting. I think it's going to be really useful. I've already used it. It's something where one can just really smoothly do very powerful data science on very large data sets right in Wolfram Language. Okay, but there's more in version 14.2. So let me tell you about some of the more that there is in version 14.2. Okay, in version 14.1, a big thing that we did was to introduce symbolic arrays. That means not just a matrix that's a 2x2 matrix with symbolic entries, but an n by n matrix where the very size of the matrix is symbolic. Okay, so we're kind of doing algebra with symbolic arrays. So there are very simple things we've done. So here we've got expand. Okay, expand doesn't do anything with dots there because it doesn't really know what to do. But array expand now does know to treat those as arrays and expand it. Now, array expand knows that this kind of operation is not commutative, so it's got a dot b plus b dot a, etc., for a matrix power. So now let's give array expand some assumptions. Let's say A is an n by n matrix. Now let's expand the adjugate of A, and we'll get the result. It's A times the determinant of A to the power n minus 2. Kind of cool. All right. Now we can also go back from okay, this is now the general case of working out the adjugate of an arbitrary matrix symbol A that is an n by n matrix, and there we see the result represented in terms of a symbolic array here. Okay, let's take our result there from expanding that matrix power. We can now use simplify. Simplify now works on symbolic arrays. We could take something like array simplify of inverse of this, and we'll get that array operation there. Now we can be a bit fancier. We can say array simplify of this combination of things, and that will just be a plus b. All of these array simplifications don't care about the dimension of the matrix. So in this particular case, it's kind of funky actually. I wonder why it's okay. So that's its representation of an arbitrary dimension identity matrix is the zeroth matrix power. But if we tell it that A is an n by n matrix, then A dot inverse of A is the n by n identity matrix. And so, for example, if we so that's the symbolic representation of an n by n identity matrix. Well, we can get fancier. We can say here is a matrix that is a symmetric matrix, an n by n symmetric matrix. And now if we do something like is that symmetric matrix symbolically equal to its transpose? The answer is yes. So that's array simplify. Another thing sort of related to this is component expand. So we've got a vector symbol, V, which is a length 2 vector. Let's say we want the components. Well, now it will tell us these are the components. These are indexed objects, V1 and V2. If we look at the input form here, we'll see that those are indexed vector symbols. Okay, so now component expand shows us why we really want symbolic arrays, because we can start expanding things. There's the 3x3 determinant expanded in terms of components. Here's matrix power expanded in terms of components. Here's cross product expanded in terms of components, and so on. And here's a slightly more elaborate thing: the inverse of M dot across product expanded as components, and there it's a more complicated kind of thing. And it will keep merrily going along with component expand. As I say, component expand, you can think of it's very useful in its own right, but it's also an ad for why you want to use truly symbolic arrays that don't require expansion to components. Okay, so that was a little bit on progress on symbolic arrays. They were a big feature in version 14.1, now expanding them in 14.2, and they'll see further expansions as we go forward to more kinds of non-commutative operations. Okay, well, every version of Wolfram Language, we make little tune-ups to the language. We always keep it compatible, but we have little things to make it more convenient to use Wolfram Language and to let Wolfram Language be a better way to describe things computationally. And sometimes these come from things I've done that I say, I always do this. So we want a function that just does that, and we make a clean design. Sometimes from elsewhere. Some often from our community, sometimes from WFRs, Wolfram Function Repository entries that people have made, and we thank people from the community who've made those function repository entries. Sometimes they're just so useful that we have to mainstream them and have that functionality built into the core language. Okay, I mentioned earlier discard. Discard is like select, except it's doing the opposite. It's discarding elements from a list. A very useful thing, particularly in data cleaning and so on. So that's a small new enhancement. Now, another one that I found really useful is something where we've extended a concept that we introduced for things like nearest and so on, of specifying what value you get back. So normally with select, we say, well, which of these are numbers? It would just give us, if we didn't do this, we'd just give us, well, which ones are numbers? But maybe I want something where I explicitly say, I want to know where the things that were numbers were. And so now I can do index there. If I do index and element here, I will get a list of the elements that were just numbers together with the indices of where those occurred. And I have to say, since we introduced this a few months ago, I've been using it all the time. Okay, so for example, we can do slightly more elaborate things. So we can say, here's 1,000,000 elements. Where's the bit vector that corresponds to the primes in those range of 1,000,000 numbers? And that's the thing that's a data structure that we can do all sorts of efficient operations on. Discard also supports the kinds of things that select supports. There it is. There's an example of that. Let's see. Well, we talked about missing fallback, this way of going through and asking for things and saying when there's a missing, fall back to something later in the missing fallback sequence of arguments, another new construct is a thing we call failsafe. So here I mapped f over this, f of 1, f of 2, that looks great. F of missing, probably not supposed to be that way. F of dollar failed, we're going to build up a bunch of symbolic crud that we really don't want. Okay, how do we deal with this? Well, there's a new function, failsafe. And failsafe says, I'm going to, if what I have being fed into me, it's a wrapper around a function. If what I have being fed into that thing is just fine, it doesn't fail, it'll just say f of 1, f of 2. But if the thing that's coming in is somehow a failure, it will simply return that failure object rather than returning f of that failure object. So this is a way of wrapping a function to make it fail safe, make the function f fail safe, so to speak. Let's see. Other language tune-ups, there's some details here. There's hold form, which doesn't hold sequences. There's now hold complete form, which also holds sequences and doesn't explicitly explode them into arguments. Another little language tune-up, I've wanted this, is counts. We've got counting the number of A, B's, oops, and C's and D's. Well, I want to count the number of things where I specify what I'm counting so that I can get, oh, there are no C's, there are no E's. This is a thing I've certainly needed repeatedly. Okay. Something that's kind of a matter of language purity, which has turned out to be quite useful, is COMAP, introduced in version 14.0. COMAP is just as map takes a function and maps it over a sequence of elements. COMAP takes a sequence of functions and co-maps them over a single element. So, for example, if you want to do 3 different things to one piece of data, use COMAP to do that. Association COMAP is new in 14.2, and it does the same thing, but now it sort of names it tells you, well, the function f, it uses as the key in an association, that gives f of x and so on. A very convenient way to just apply something to a bunch of data. So, for example, here we're saying, what are the sine, cos, tan values of pi over 3? And there we get sort of the table of results. Okay. Next up, something that seems like a detail, but it's really, I've decided it's something I really like, is spiffing up colors. We introduced our current default colors for plots in version 10. That was basically a decade ago. And well, things have changed in the last decade. You know, the world's changed, fashions have changed, color preferences have changed, displays have changed, and so on. It's time for a refresh. You know, it's the 2025 fashion season, so to speak, for colors for our default plots. And so in version 14.2, we have brightened up our colors. We'll be continuing to do that across our visualization. We've brightened up our default colors. You can always get the legacy colors if you want them. I have to say, we discovered that after we introduced the colors we introduced in 10 years ago, that a large number of other systems that do various kinds of visualization copied our colors. So I suppose it's flattering, but it's sort of amusing. So these are the new colors. They're spiffier. You know, I write lots of posts, and I was finding I kept on having to sort of adjust my colors to be non-standard colors in my posts because I didn't think they looked good enough. Now with our new spiffed up colors, I'm like, this is great. The default is exactly what I want. And well, you can see it here with a few more colors being used. This is kind of the brightened colors for our time. And histograms also got brightened, and there's the comparison for histograms. If you can see it through the different layers of transmission here, that's the old one, that's the new one. We've just brightened them up a bit. Still very recognizable, but just a bit brighter and spiffier. Actually, if you look at the comparison, here we're doing an explicit comparison between the color data, default plot color V10, default plot colors for now. You can see it's pretty subtle changes, but they're important to the visual perception of our visualizations. Okay, different topic, LLMs. I mentioned the Notebook Assistant. That's sort of the big news, but another thing we have, partly to support Notebook Assistant functionality, partly for other reasons, we've kind of been progressively beefing up our language mechanisms for dealing with LLMs. We introduced LLM function back in the middle of 2023, very soon after LLMs appeared. With LLM Kit, you can now use all those functions in a very seamless way, sort of zero hassle setup for those functions. There are two new functions in version 14.2, LLM Synthesize Submit and Chat Submit. They are for doing asynchronous interaction with LLMs. They follow Cloud Submit and URL Submit, which are asynchronous operations. Now, this is a little tricky to demo, but I'll see whether I can do it. Let me see. See how best to do this. Well, let's see. First of all, I'm going to say C equals a null list and then synthesize, submit a one-liner about a wolf. I'm going to bring back a handler function, which is a content chunk received, and I'm going to make the separate chunks about the wolf. So there's a task object that was generated from the submission, and now I'm going to ask, well, what is C at the end of that? Now the task has the task run. What am I looking for here? I should expect that. Is it finished? Well, let's just try running it again. There we go. It hadn't finished when I asked for C before. This asynchronous stuff is always quite confusing. So now these are the separate chunks that came in from the LLM as it was writing its one-liner about a wolf. Okay, so actually we can see that happening dynamically. Let's say we set a variable S that is a null string, and we say dynamic of S. So right now you don't see anything there. Okay, now let me enter LLM synthesize, submit a paragraph about a wolf. So now the handler function is going to be content chunk received, and when it receives that chunk, it's going to set S to what S was before together with that content chunk. So we'll see the S here. If you watch carefully, you'll see that S coming in dynamically as, okay, there's the task object. Now it's writing. If you saw that, it progressively wrote that paragraph as chunks were received, and the handler function wrote them, and the dynamic showed what the handler function was doing. Okay, so that's asynchronous use of LLMs. Chat submit is the analog for the chat mechanism, chat evaluate, and so on. Of chat submit is to chat evaluate, as cloud submit is to cloud evaluate, etc. And LLM synthesize submit is to LLM synthesize. Okay, next, bit of infrastructure. This is about launching kernels. So I do lots of parallel computation. I don't know, this may be very scary because I'm not in my usual location. So many of my machines are thousands of miles away, but let's see what happens. Okay, this is now launching on my various machines, and you see all these different kernels being launched. There are probably a couple of hundred of them being launched in parallel here. This is kind of a new thing in version 14.2, is the parallel launching of parallel kernels. And oh, whoops, oh dear. Well, that's what happens if the machines are thousands of miles away. Occasionally they drop packets. Oh well. But actually, it's very good at recovering from dropped packets. And I'm sure if I just tell it to do a parallel computation now, even though my machines are scattered around the country, it probably will be able to go, okay, it got 203 kernels. I think there's like 220 something total. So it missed a few, but it'll nicely, robustly be able to do the computation, even though some of those kernels didn't show up. By the way, a small thing for version 14.2, parallel select and parallel cases Parallel select is important because it only returns to the master kernel the things which were selected. So the uh, um, even if the let's try and kill this. Um, um, even if even if there were lots of things being sampled in the select, it only um, it only um, it only actually returns the ones that were selected. Okay. Oh, there we go. Finally aborted. Okay. All right. We're filling this session up with all kinds of crud. We've got 5 GB of um, kind of foolishly expanded tabular data and other things. All right. Let's move to a different topic. Let's talk about video. Video is a thing that we've been progressively expanding in recent versions. So here we have a video. There's a video. We can play this video if we want to. It's kind of a video of a bunch of people wandering around. Now, we could take an individual frame and we could say, well, what we want to do here is we take we could take an individual frame and we could operate on it. But here now, image bounding boxes is operating on the whole video using a GPU. In this case, I hope I have a GPU on this machine. I'm not sure if I do, but anyway, so it's running. Okay, there we go. Processing video frames. Now it's, oh dear, it's taking a long time to do that. But now it's processing these video frames, finding image bounding boxes in that video. And then if we say from that, we say we're going to be highlighting the video and we're going to find the image bounding boxes in that video. And what will happen is those image bounding boxes will show the individual people in this video. Okay, so let's try it. We're going to now highlight that video. So it's going to create a new video. It takes a little while to create the video. And what we'll see in the finished video is hopefully a bunch of boxes indicating the individual people walking around in these frames. Now, where are we going with all of this? Image bounding boxes individually tracks the people in those separate frames. And by the way, the fact that we can do this directly on the video, I think that's new in 14.2. That I think before that we had to map over the frames explicitly. But okay, so now we've got this video and it's got these bounding boxes indicated for all these people. Okay, but what if you want to track the individual people? What if you want to track that that lady, I think, in or that chap there or whatever? What if you want to track these individual people and follow an individual in these pictures? Doesn't have to be a person, could be a rhinoceros, could be a ball, could be lots of different things. Well, for that, you need to use a new function in version 14.2, video object tracking. So let's watch this work. Okay, now it's going to process these frames, and now it's not just, it's going to take a little bit more work here because it's going to be tracking each individual person and seeing where they went, rather than just saying there's a person there in that frame. So it's tracking across frames different people. So let's see, and this, let's see, I'm going to get the objects here. I'm going to track the all these different objects. Let's take a look here. Okay, it's taking a little longer to do this. I'm going to then generate a video from this. We go ahead and get that queued up, ready to go. As soon as this finishes, we'll generate a video from that list of objects. But then we're going to have this tracking list. And the tracking list, we can do all sorts of other operations on. So let's take a look and see what we can do with all of this. Okay, hold on. It's going to come. It's going to come. I might ask for questions, except by the time we've got a question, we'll have finished this this piece of video tracking. But let's continue to see that go. um, the come on, track. You can follow that person. Um, and obviously you can do this, with something like, what is this? Oh my gosh, it said it was 8 hours and now it's zipped down to a few seconds. That's a good sign. Okay, we got it. Um, all right, let's now make a video from that. Hopefully this won't take too long. This looks like it's a modest amount of time. We can see already in the preview there that we're going to have nice color boxes there. Let's see. Run. I do like these progress monitors. This is something we've introduced in recent versions for an increasing number of functions. These progress monitors just sort of show what they're doing, and when it's done, they go away. And many of them, like this one, can give you a pretty accurate estimated time to completion of the task. Okay, here we go. Now we should have a video. Here we have a video, and now this video, we can see we got color coding for each person, and this is individually tracking each person. So now, not only can we track the people, but we can ask for what kinds of objects do we actually have in this video. So let's count by labels our objects. And we have 95 people, 11 backpacks, 13 handbags, 1 ski, and 1 domestic dog. So let's figure out, let's try and find the domestic dog. Let's look at our objects. Let's ask for the time interval in which the domestic dog appears. So it's not very long. Look at that. It's just a fraction of a second. There is a dog. So now let's go ahead and try and find the dog. And I didn't notice the dog. I mean, it's kind of like one of those psychology experiments where the person comes out in the gorilla suit. But okay, we've got a dog here. Now, where is the dog? I think that might be the dog there. Let's see, where is the dog? Or is it that a backpack? Maybe there isn't really a dog. I don't know. Oh yes, okay. Let's see where it thought the dog was. So let's go ahead and take that. Oh, I was right. Well, maybe it's just a backpack. Maybe there's no dog in the picture. It kind of looks like a dog, doesn't it? But yeah, look at that. There's the nose, etc. But maybe it's actually a backpack. Well, that's life with machine learning. But in any case, it's pretty cool that we can do this tracking and figure out, where's the dog or the non-dog, as the case may be, in these video frames. All right. Next topic, totally new area for us, game theory. Game theory is one of those techniques that gets used in different places. I think it's used when it can be used. It's like, when can you find the exact solution to some mathematical problem? Game theory is sort of one of these cases where there's sort of you carve off certain kinds of problems for which there are sort of game theoretic solutions. There are many problems for which there are not, but when you can find one which has a game theoretic solution, you kind of have it made because you can sort of solve things. Okay, so how do we represent game theory in Wolfram Language? That was sort of a challenge for many years, and there are many packages people have built for game theory using a variety of different methods for representing games. We've tried to have the best, strongest, cleanest method. So here's a matrix game, and this is a zero-sum two-player game, and those are the payoffs in the game, and we'll see those a little bit. Let's make a data set based on that, and we'll see there's player 1, player 2, and these are the different actions here, and this is the payoffs to player 1 and player 2 based on these different actions here. So, okay, another way to plot the game is with a matrix game plot, and this shows us for player 1 and player 2, this shows us the payoffs for each player for each of the different actions in each case here. And so what can you do with with these games? Well, you can solve these games. You can find optimal strategies for these games. In particular, you can find a solution that maximizes the expected payoffs for all the players, the so-called Nash equilibrium. Actually, it's a little footnote to history that John Nash was a longtime user of Mathematica, came to quite a few of our conferences. I unfortunately never ran into him myself. Actually, I had run into him much earlier when I was at the Institute for Advanced Study in Princeton, but he wasn't in a particularly good phase of life at that time. But subsequently, he came to a bunch of our conferences. So small kind of footnote to history and connection back. We finally now have Nash equilibria as built-in features of Wolfram Language. Okay, so how does that work? Well, we can say find matrix game strategies for this matrix game, and now it gives us this representation of the probabilities. So it says that player 1 should play action 1 with probability 5/11ths, et cetera, et cetera, et cetera. Okay, so then the question might be, what are the expected payoffs for these players if they play lots of games with those probabilities? What are their expected payoffs? And there's the answer. So it's sometimes kind of hard to keep track of what all these different players and actions and so on are. So here we have a matrix game where we've labeled the players with a wolf and a ram in that particular case, and the cooperating defect. And so here now we have this is showing the wolf and the ram in that case, and giving us some more labeling that we can use as we index into this game. So another thing we have is game theory data. We've taken sort of all the standard games that you might use in a course about game theory, and we now have computable versions of them. This is the L for all bar game, the case of the 4-player case of that. And here's a data set of that. I'm sure if we ask for the 6-player case, it'll give us. Oh, it kind of punted in the end on doing that with different colors. But anyway, there's the 4-player case of that particular game, and now we can do all of these functions because this is Wolfram Language and it's got lots of powerful underlying algorithms. There we get the exact solution for the strategies for this game involving these square roots and things like this. So now we can make a matrix game plot of this. This is what it does when this is a 5-player game, and we're showing. Let's see, what are we showing here? We're showing the 50th game solution. Yeah, that's what that 50 means for this particular game. So each of these was a possible game solution. This is the 50th one for this 5-player game, and it nicely shows the result there. Now, we can also say, when we do find matrix game strategies, that we can give a matrix game with exact numbers here, and it'll compute the game strategies, again, with exact numbers. Well, that's matrix games. We can also look at tree games, where there's a tree of possibilities. So this is player A plays, then player B plays, and each one has different possible plays that they can make, and we can then find the tree game strategies for that tree game, and we can make a tree game plot of a particular game. This is the escalation game, and this is now showing how that works. Actually, I made some studies of games recently where I was studying using multi-way systems to study games, studying things like tic-tac-toe. One of the features of games, as normally done in game theory, is that sort of every separate move is somehow a distinct kind of thing. Whereas in something like tic-tac-toe, or for that matter, chess or something, sort of you are in the same you have the same set of moves at every turn, and that's a little bit different. And that's something that you can study nicely with multi-way graphs, and maybe there'll be a merger of those things in a future Wolfram Language version. Okay, next topic. Let's talk about astronomy. So we've introduced pretty powerful astronomy capabilities in the last couple of versions. What's new in version 14.2 is computing syzygies and a variety of other things. So a syzygy is when astronomical objects line up, or at least line up from where you are. So when there's an eclipse, that's a syzygy. The Earth and the Moon, the Sun and the Moon are lining up. There are lots of different syzygies. The September equinox is when or the autumnal equinox, as it's called in the Northern Hemisphere, is when the plane of the ecliptic lines up. I'm forgetting what this is. Well, operationally, it's when the day and night are of equal length. And this now computes that. That's yeah, it's okay. It's when the the plane of the ecliptic crosses the celestial equator, i.e., the projection of the Earth's equator. And for example, we can say, okay, at the autumnal equinox, show us where the sun actually is, and we can actually see, look, there's the sun, and there's the equator, the celestial equator, and there's the plane of the ecliptic, and look, this is the moment at which the sun is at the place where the plane of the ecliptic crosses the celestial, the plane of the celestial equator. Okay, well, so now another astro event. We can find what's the global minimum distance between Jupiter and Saturn in the next 100 years. So now we compute that. Okay, it's in 2080 and that time. So let's go ahead and make an astrographics of that. Let's show Jupiter and Saturn in the sky. And it's kind of cool because this is a time when they're so close that their moons almost overlap in what you could see through a telescope. So if you're around in 2080, check it out. So there are lots of special names that have been given to these different astronomical configurations. I guess people, particularly in the past, were thought these things were really cool and looked for them. So this is a periposeidium. So something like a perigee is when you are closest to the Earth, Gaia, Geo, the geoid, etc. Perihelion is when you're closest to the sun. Periposeidium is when you're closest to Neptune. So this is going to find the time when the moon Triton is closest to Neptune. Well, there's a very famous example of precision computation of peri things, which is the perihelion of Mercury. So if we look between the years 1800 and 1820, these are all the perihelions of Mercury at that time. Okay, so those are the astro positions of the perihelion of Mercury, and this is where Mercury was at each of its perihelions between 1800 and 1820. Okay, let's plot those. Okay, so let's plot those on the sky in a reference frame where in the plane of the ecliptic, that's where relative to the sun, where Mercury was on the sky in the plane of the ecliptic and the orbital plane of the Earth and so on. Okay, so we can go ahead here and make a table of the times of those perihelions. There are let's see, those are the first two perihelions. And now we can say how far apart was Mercury at the times of those perihelions. So that's telling us, sorry, that's the perihelions from the year 1800 to the year 1900. Sorry, that's a century apart in perihelions, 0.159 degrees angular separation between those perihelions. Okay, and now what we want to do is to compute. So let me explain something. In a perfect inverse square law of gravity with idealized planets, the perihelion always lines up. So for example, the Earth is always at the same place, almost precisely at the same, not precisely, but almost precisely at the same place in its orbit around the sun at the time when it is closest to the sun. The elliptical orbit, the ellipse does not precess. Well, it does precess a bit, but in sort of the simplest way of setting things up, with a perfect inverse square law, the ellipse does not precess. So any change in the perihelion of Mercury is evidence of something that is beyond the idealized planet inverse square law story. So what we see is the perihelion of Mercury advances by 0.15 degrees in a century between 1800 and 1900. And so we can say how many, let's see, we can look at the difference between those things per day, and then we can look at that in arc seconds per century, and it is advancing by 574 arc seconds per century. Okay, well, there are all kinds of effects that contribute to this. The effect of Jupiter tugging on Mercury, Venus tugging on Mercury, things like this. But 43 arc seconds per century in the late 1800s was not accounted for in the advance of the perihelion of Mercury. What was it? Was it the flattening of the sun? Was it whatever? Turns out it was a general relativistic effect. It's evidence for the validity of general relativity that there is this additional advance of the perihelion of Mercury. Something I'm really interested in is finding those subtle effects now that reveal the discreteness of space and features of our physics project. But that's a quite different story. But for now, it's pretty neat that with just a few lines, we can compute the advance of the perihelion of Mercury over the course of a century and so on. All right, some more physicsy stuff. PDEs. We've been doing a lot with PDEs, and we've been progressively adding more and more domains for PDE modeling, from acoustics to fluid dynamics to other kinds of things. In version 14.2, we're adding static and quasi-static magnetic fields. So this is now saying I'm going to set up a PDE, and really the thing that's tricky is this modeling specification of the magnetization is a piecewise function of whether the thing is inside this region or not. There's a magnetic potential condition on the edges. This is the tricky stuff to set up. Well, then you also have the trickiness of actually solving the equations, but that happened really quickly here. We just used ND solve value. Now we're going to plot the field lines for this magnetic object. So this is now plotting for this weird shaped magnet. This is plotting the magnetic field lines. It's pretty neat that one can do that as straightforwardly as this. PDE modeling is really complicated. We've made it very much easier to do with the whole modeling language and geometric computational geometry that we have in Wolfram Language. But we've also been adding a lot of information and documentation to this. We've been basically writing monographs about PDE modeling in different domains. There's another 200 pages of textbook style documentation for lots of different domains now added in version 14.2. Well, another topic, features in graphics and geometry and graphs and things. So here's the thing we added. We can make a region out of a filled curve. So whatever that curve is, we can turn it into a region, and we can compute things like the area of that region. We can just put in this thing and we can compute it's a region object. We can compute its area. Some useful things from that. Let's say we have the letter A. We can compute now the region size of the letter A. Other sort of geometry kinds of things we can do. Let's take a 3D molecule plot of, I don't know, ATP, and let's now make a new thing, a molecule mesh. So this is now a region that represents, this is kind of the schematic for ATP. This is now a region that represents kind of, and we have a variety of ways to make these regions, kind of a region of the sort of where the electrons are can be in ATP. And then we can take that and we can do computational geometry on it. And that's relevant because we can start to do operations like figuring out sort of how far away some other molecule that's a certain distance away from this, how far away is it from the ATP? If we have another molecule and we want to sort of rearrange it and figure out how closely they dock and so on, we can start to do that, those kinds of things. So this is a merger of computational geometry and computational chemistry. One of the things that sort of is possible in Wolfram Language with all of its integrated capabilities. Another sort of minor thing that's I kind of like, because I'm going to use it a bunch, in when we make a graph, a layered graph, we have to kind of guess what the graph is supposed to be about. So there are different kinds of embeddings that are useful for different kinds of meanings for graphs. So this is symmetric layered embedding, just takes that graph. If we happen to know that we want to think about it as a symmetric graph, which we might not, then we can use symmetric layered embedding and it'll look nice and symmetrical. Sometimes the graph drawing system will automatically figure out that that's how things should work. Okay, let's talk about user interface kinds of tune-ups. So let's say I say plot sine x, and we see all the syntax coloring going on as I type. And now I type frame label, and I can never remember what the settings for the frame label option are. But now, look at that. We get a little autocomplete there. Oops, the autocomplete goes away if I try and scroll it. We get a little autocomplete there that now has prompting that says, okay, bottom left. All right, we fill that in. Now we can type in, something where we tab to the next space, and we can, oops, I typed form object. I don't know why, but oh, that was a frame label, which I didn't even have a frame. That was not a very good example, actually, because there isn't even a frame in this plot because I didn't tell it to use a frame. But there, now I did. And now I've got those labels. So this is a kind of enhancement to our autocomplete mechanism, kind of prompting one for what the different entries in in an option value are. There's all kinds of enhancements to autocomplete. There's some enhancements to the way that we preview notebooks in iOS and the Finder and so on, that there's now a preview image of the notebook that's visible in the Finder. It's another user interface feature. Another thing that you won't really see for real here, but you'll begin to see the little sort of proto pieces. There's a function called light dark switched now, as long with a thing called theme color. Those are the beginnings of the hooks to make a full generalized dark mode for Wolfram Language, which will be coming in the next version. But those are the initial hooks for doing that, and you can play with them if you want to. Light dark switched is basically something which is a representation of a color or other option value, where it is, if you're in light mode, it's this, if you're in dark mode, it's that. Okay, we're getting close to the end here. Another thing that's new is GPU support. We have long had support for GPUs inside operations like machine learning, like linear algebra, and so on. But there's sort of a question of do-it-yourself GPUism. And we've had CUDA support for a long time. We are steadily integrating GPUs into the compiler and into other aspects of what you have in the language. Now, I'm not completely certain that the computer I have here has a GPU, but let's hope for the best. Okay, so we're going to say V is this GPU array. Okay, it did have a GPU. Checked for GPU compatibility and it found it happy. So this is putting 10 million elements into video RAM, into GPU memory. And once that data is in GPU memory, it can be much more efficiently manipulated with operations that can be done on the GPU. So here, for example, this is an operation that can be done zippingly fast directly on the GPU. And if we do that on the GPU, there we go, we'll find it happens in 0.009 seconds. If we were to do the same thing with a CPU, we could, let's see, the CPU result. Well, okay, that was a GPU array that contained random reals. Let's do the corresponding. So with a CPU, we set the thing to random real, not inside a GPU array. We do the repeated timing. We're waiting. Okay, it was about a bit more than 10 times slower. So in this case, moving our 10 million elements into GPU memory and then being able to do GPU operations on them. And we're sort of automatically compiling these things to be run on the GPU for certain operations. It's only some operations that will work directly on the GPU. Others will have to be done in the CPU. We'll have to move the data back from the GPU to the CPU. We're steadily increasing the number of operations that can be done directly in the GPU. And that's something, again, that you can control with the compiler. All right, other things. Well, let's see, a few other operations, few other things we've got mid-date. That's find the middle of something. Find the thing that's the week that's 2/3 of the way through the year 2025. You'll see a bunch of other mid functions coming soon, but mid-date is our first one. Another thing, things like surface integrate now work with vector symbols. So we can just directly say integrate x.x over the surface of a cone, and we get the result there. I think that's pretty neat. Things like sum convergence now let you give the domain of variables, and you get results with conditions on the variables. A little convenience I wanted is digit count, counting the number of ones in, let's say, the binary decomposition of a number. Now it will say how long the number can be. So how many leading zeros it's going to be padded with. That's just a convenient thing in using digit count to have that, a very minor update. Another thing, kind of a detail, but can be very important. Take largest by default uses numerical order. So it finds the numerical values of these quantities to figure out which one is largest. But sometimes we don't want the numerical order. We just want the sort order. And then we'll get different results from take largest by using the sort order. So now we've got an argument to take largest that lets you specify how it should do the ordering. Okay, well now we're into the details here. I mean, I should say that in version 14.2, we made lots of changes. I mean, we had let's see, we had 80 completely new functions, 177 functions that have been substantially updated, thousands of bugs that have been fixed, lots of things like that. We're now kind of in the details section because I'm down to moon phases. We added new capabilities for figuring out new properties of moon phases, new methods for computing exactly what you mean by the phase of the moon, and so on. That's down in the details, but if you need it, you need it. And that's the story of version 14.2. We've been working on these capabilities, in some cases, only for over the last year, in a few cases, only in the time since version 14.1 came out. But what we do in general is we have kind of a portfolio of R&D, of research and development activities that we're doing, which range in length from a few months to many years. And so there are things that we're now seeing maturing, like Tabular, for example, which has been in development for many years. And finally, in version 14.2, it's ready. We can release it, and we're excited to let people use it. So that's the story of version 14.2, and you can get it today. It's ready. Download it. If you're using the cloud, it's already in the cloud. You can be running version 14.2 in the cloud, download it to the desktop, get it in Wolfram 1, get it in Mathematica. You can use all the things that I've been showing you immediately today. So, well, I hoped you liked that summary of version 14.2. We work really hard on these things, and it's it's really I'm pretty pleased with the things that we've been able to do here, and hope that people will be able to use them well, and hope that people will, if they know how to use it, use our computational language. It's become really easier for people to get into our computational language by using the Notebook Assistant. You really don't have to understand things to get started. You can just sort of chat with the Notebook Assistant, and that's a great way to get started. Encourage your colleagues and friends to use Wolfram Language. Give them the on-ramp of the Notebook Assistant. If you get Notebook Assistant, I think we still have a plan going where you get a couple of free subscriptions for trial subscriptions to give to your colleagues and friends. Please spread the word about what we've been doing for the last 40 years or so. I'm pretty excited with the kind of tower of technology that we built. Version 14.2 is the latest instance of all of that. All right, so thanks very much. I see a few questions here. I think I may have time. Let me find out. Okay. I think I'm supposed to go to another event here, but let me see if I can just address one or two questions really quickly. Lulu asks, what's the most exciting update? Tabular. Powell asks, can you create composite tables from multiple tables by matching columns and values? I think the answer to that is yes. Let's see. There's a commenter from, I don't think I even know what Wolfram commenter is, so I can tell you it's not me. File comments, column-wise thread is neat, thank you. Sleepy comments, is it planned to expand Fourier, the Fourier function, to transform along a specified axis? Right now, it requires a bunch of transposes. That's an interesting suggestion. We should look into that. I don't know. We did make some changes to Fourier in version 14.2, but I don't think they're along those lines. Sleepy also asks, are we going to add support for local LLMs or specifying an explicit endpoint? Okay, so let me explain that. There is already, we have been very actively working on local LLMs. I'm not sure if anything is released yet. If it isn't released now, it will be released very soon. The ability to use a local LLM with Wolfram Language is both directly, here are the neural net weights, and here's a kind of local server that you can set up. There's a function repository entry for OLLAMA synthesize, which is using a local LLM here. This is a local server set up with a local LLM, but this will get more integrated going forward. In terms of using external APIs, yes, we have lots of capability for using external APIs, but the Notebook Assistant is really a big stack of technology that isn't just a connection to an LLM. It's really a quite elaborate piece of technology. So it's not something where you can just sort of expect to use it with your LLM of your choice. You can access an LLM of your choice and use that. And we've been connecting with many different LLMs. This is our benchmarking project where we update every week. What's the best performance was updated yesterday? The best performing LLMs on writing Wolfram language code. And you can see different rankings here. There are lots of LLMs. We connect to all of these. And you can use any of them. If you have an account with these, you can use any of these as raw LLMs within LLM function and other functionality in Wolfram language. The Notebook Assistant is using our own elaborately harnessed LLM to do what it does. Let's see. Sleepy is asking, does Fourier work with GPU arrays? I believe the answer is yes. I believe you can do Fourier transforms directly on GPU arrays. Now, that's a little tricky because depending on what type of machine you have, there may be different things supported in the GPU. That is all documented, but I don't know offhand exactly how that works. Let's see. K-pop is asking, what's used for tracking bounding boxes? It's, I believe, a neural net. It's the latest and greatest methodology for doing those kinds of things. All right. Well, thanks for those questions, and thanks for joining me for a quick look at, well, it wasn't so quick actually, for a look at version 14.2. Get it, download it, tell people about it, tell us what you think of it, and have fun, invent, discover, learn lots of great things with version 14.2. Thanks a lot, and bye for now.